going to continue today with conversion of units, and we'll go and wrap up this chapter 0, I'm calling it, and move on into chapter 1 where we get into motion and balance. But I have a couple more things, just conversion of units. This is really just an application of dimensional analysis. So say, for example, I have 24 meters per second, and I want to convert it to miles per hour. Or vice versa, if you want to convert miles per hour to meters per second, how would you do that? You use what we call conversion factors. And a conversion factor just says that one unit is equal to so much of another unit. So for example, 1 mile is equal to, does anybody know how many meters is in a mile? You guys know, we got a bunch of track stars. Yeah, a mile. It is 16 something. It's not quite, it's 1609. Who's that, Myosha? Yeah, so it's 1609. Not quite, or a little more than 1600 meters. That's 4 laps around, your 400 meter track. So 1609 meters, and an hour is equal to, let's see, there are 60 seconds in a minute, there are 60 minutes in an hour, so that's how many seconds? $36,000. 3,600. Yeah, so 1 hour is 3,600 seconds. Listen, you don't have to know those conversion factors. If there are any conversion factors, I'll give them to you. Though you do need to know the metric prefixes that I showed you last time. Remember, there's just 3 of them, right? There was milli, centi, and kilo. Milli is 1,000, or 10 to the negative 3. Centi is 100, or 1 over 100, or 10 to the minus 2. And kilo is 1,000, or 10 to the 3rd. I'll do one of those for you in just a bit. So I would set this up. I would say 24 meters per second. And then I would multiply it by my conversion factors. I would have something to convert the distance. Now, I want to set up my conversion factor with either miles or meters in the numerator and either miles or meters in the denominator. What am I going to put in the denominator here to get rid of my meters? Am I going to put miles or meters here? I'm going to put meters, and then I'll put miles here. So I'll have 1 mile over 1609 meters. And then in a similar way, if I want to convert seconds, what am I going to put in the denominator here, in the bottom part of the fraction? I'm going to put hours, right? And so I have 1 hour is 3,600 seconds. And then I can go back and I can cancel out some units. My seconds cancel here and here. My meters cancel here and here. And I'm left with miles per hour. We haven't changed the nature of the measurement because these conversion factors have not a value equal to 1, but they have a meaning equal to 1 because 3,600 seconds is equal to 1 hour. So it's as if you can think of, I'm just sort of multiplying this thing by 1, although the value isn't 1, it's just the meaning of it is 1. These two are equal, so they have a unity value. You follow what I'm saying? You haven't changed the nature of the measurement, you've just changed the units of it. And so this is what it is. I don't think I have my calculator. Anybody tell me what that is? Look at this. What's your name? Taylor, right? What is it? Do you know? Okay, we'll just call it 54 miles per hour. All right, 54 miles per hour. So that's kind of useful because, next time you're out and you're driving 50 miles an hour, you can look over to your passengers like, man, I'm zooming along at 25 meters per second. And then they'll just sort of look at you. What are you talking about? Okay? But you can do that unit conversion. And it is quite important, actually, to know how to do these unit conversions as you're dealing with different measurements. Okay, let's try these 2 clicker questions. Again, we're using frequency code AA. That's the default on your clicker. Let's try this one on the left first. Irene is 2 meters tall. A building is 10 meters tall. How tall is the building in the unit of Irene? That is, how many Irenes would you need to stack up in order to measure the same height of the building? I know not everybody has the workbook yet, but can y'all see in the back? Lydia, can you see it okay? We're doing the one on the left, and then right after that, we'll do the one on the right. All right, we're going to stop at 52 seconds, 52. Just guess if you don't know. The one on the left. I'm sorry, what? Yeah, this is the Irene. All right, I'll stop at 102. These questions, by the way, I took from an old test. So you'll have similar questions on your exam, which is coming up. I don't know, when is it coming up, actually? February 2nd, in 2 weeks from today, is that right? Awesome. Don't y'all love exams? Oh, I hate exams. But they really are a nice checkpoint for you to see if you know the material. All right, so why do gorillas have big nostrils? They got big fingers. Really? Y'all know that she is like an awesome long jumper? She can jump like 18 feet. That was a bad day. Can you imagine 18 feet? That's like 1, 2, 3, 4. That's like from here over to that wall. Right? Isn't that right? Oh, sorry, she's blushing. But that's awesome. 18. Who here can jump 18 feet? Yeah, seriously. All right. Um, all right, let's do this next one. What is the unit for mass in the Sistine Internationale Convention? You can ask your neighbor if you like. Looks like you all know. I'm going to stop at 25. 25. Okay, awesome. That's C is the right. That was an easy one, right? Yeah, they were easy. So kilograms, and in particular, that's in the MKS system. So really, I should make a stipulation here that's in the MKS system. What is the unit in the CGS system for mass? Remember, in the SI system, you have the MKS, which is the one that we'll use. That's typical in physics. But in the health sciences, you usually use the CGS system. What does G stand for there? Grams, right? Because, you use centimeters. And you use grams some, but you use centimeters a lot. Um, where do you find a dog with one leg? Right where you left them. I'm sorry, is that a mean joke? That's kind of mean. Sorry. I'm a mean guy. Let's try this. We can have unit conversions just between nonsensical units, kind of like we did with Irene here. Although this one, it doesn't work out quite as easily. If I have this as my unit conversion factor, and I want to know 225 meters is equal to how many smoots, I say 225 meters times my unit conversion factor. I do 125 meters, 364.4 smoots, and then that's equal to, well, what is that equal to? 656. That looks right to me. So we'll just call it 660 smoots. There was actually a guy, a famous guy, who won the Nobel Prize a number of years ago, and he went to some school up north, like in Boston or whatever, and he was in this fraternity, and part of the ritual of joining this fraternity is that you measured this famous bridge in Boston in smoots, or in whatever your name was. This guy's name was Smoot, and so they'd make you go out and lay you down head to toe all along the bridge until they measured the exact length of the bridge and your height. We could do that here. We could measure the width of the room in Haley. How many Haleys across is this room? but the floor is kind of dirty, so we won't do that today. All right. Also, you do need to know how to convert metric prefixes. So let's say that I have, for example, 243 grams, and I want to know how many kilograms is this. All right, so in order to do that, well, when you get good at this, you'll just say, well, 243 grams, all I got to do is just move that decimal place over 1, 2, 3 spots, and it's going to be 0.243 kilograms. But if you want to go through it more rigorously, you'd say 243 grams times 1 kilogram is equal to 10 to the third grams. That comes from my metric prefixes that you need to know. That is milli, centi, and kilo, 10 to the minus 3, 10 to the minus 2, and 10 to the third. And so that's where this 10 to the third comes from. And then this is equal to 0.243 kilograms. In a similar way, let's say that we wanted to convert 25 centimeters to meters. Well, gosh, you might be able to just think about that. How many meters is 25 centimeters equal to? Well, how many centimeters are in a meter? How big is a centimeter? Can you show me, like, is it this big? Is it this big? What is it? It's about the width of your pinky, right? It's about this. A centimeter is about that. And how many of those, then, are in a meter? We know a meter is about this long. How many of those are in a meter? There are 100 centimeters in a meter. And that's where this metric prefix comes in. It's actually 1 over 100, or 1 over 10 squared, which is 1 over 100. So there are 100 centimeters in 1 meter. And so we can do, oh, so how many meters is 25 centimeters equal to? How many? No. You're going the wrong way. 0.25, right. So think about these as you go along, because 2,500 centimeters would be 25 meters. But 0.25 meters is the same. A quarter of a meter is 25 centimeters. But again, if you want to do this rigorously, you would say 25 centimeters, and then multiply it by your conversion factor. 1 centimeter is equal to 10 to the minus 2 meters, and then that would be 0.25 meters. Or you could do it a slightly different way. You could say 25 centimeters, my unit conversion factor, 1 meter is 100 centimeters. And that would give you the same answer. Okay? But you just need to know these metric prefixes. There'll be a very simple question, something like one of these. Or, you know, it's simple if you know how to do it. But if you don't know how to do it, then it's difficult. Okie dokie? You're good on metric prefixes? We're not going to use them a lot, but you might see one question on the upcoming exam in 2 weeks that's related to that. May I go on to the next page? All right. We're starting on the next chapter. So I'll be, as I said, I like to follow along with the book pretty closely here. This chapter deals with largely the laws of motion, and we'll get into forces and torques, and we'll see how forces act in the body and how we can use various things like simple machines to change or alter the direction of forces. But first, let's just sort of summarize the laws of motion. Did you know that the laws of motion weren't conceived of until, gosh, like the 1700s when Isaac Newton came about? And y'all know Isaac Newton, right? Heard of Newton? By the way, do you know what Isaac Newton is famous for? Well, he's famous for the laws of motion, right? But there's something else that he created, he invented, that literally changed the way that you live today. Well, he described gravity, yeah. And, you know, I guess that probably changed your life, but more fundamentally is he created or invented the study of calculus. I know y'all don't take calculus, but, you know, calculus is sort of the bedrock for a lot of the scientific studies that we do for building this building, and for building big skyscrapers and making your cell phones and your calculators. Isaac Newton invented calculus, and it really changed the world from that point forward in the way that we live. It made possible a lot of the things that we have today that we just sort of take for granted, that he invented calculus. It's an interesting fact that Isaac Newton, he invented calculus in England, but there was another guy, what was his name? Leibniz. People don't even know Leibniz. But he was sort of up in northern Europe, sort of the Scandinavian region, I think. He also invented calculus. But he and Isaac Newton, they never talked, but they did it at almost exactly the same time. And so there are people that say, don't write this down, I'm not going to test you on it, but I just think it's interesting. There are people that say that in the course of history, there are times when ideas are just ripe for discovery. So they would say, Isaac Newton, yes, he was a genius, and he knew a lot, and he was able to develop a lot of these ideas. And Leibniz, he was a genius, but the time was ripe for people to discover calculus at that time. Isn't that cool? I don't know that I believe that, but it's kind of a cool idea to think about. All right, so his laws of motion, you probably covered these in, sixth grade or whatever, but let's go over them because you probably don't really understand them, and you probably don't really believe them. Because prior to Isaac Newton's age, people believed in a system, the Aristotelian system, and the Aristotelian system was much different, like Aristotle. But the Aristotelian system of belief about motion was quite a bit different from the Newtonian system. And you know what you are? You're an Aristotelian. You're not a Newtonian thinker. You really think like Aristotle. I know that you do because almost everybody does. You think about motion in terms of Aristotle's ideas, not in terms of Newton. All right, so the first law is the law of inertia. All right, and inertia is a measure of an object's mass it describes an object's tendency to stay in its current state of motion. So Newton said, if an object is at rest, it will stay at rest. If an object is moving, it will continue moving forever. It will never stop. If an object has inertia, whatever it's doing at that point is what it's going to continue doing. And that's very different from what Aristotle said. Aristotle said that an object's natural state, he sort of believed in these natural states, that physical objects have states that they prefer to be in. He said that an object's natural state is to be what? Is to be in motion or at rest. What is an object's natural state according to Aristotle? To be in motion or at rest? What do you think? At rest, right? Because we look around and almost everything that we see is at rest, right? And even Aristotle would say, well, if I push this desk, I give it motion. Well, look, that Newton, he's great. He doesn't know anything. Did you like how I threw that word out? Did it connect with you? It's short for crazy. That Newton is crazy because this desk, it doesn't go on forever. That's the most ludicrous idea that I've ever heard, though they didn't live in the same time, so they didn't actually talk. But he would say that's absurd. That they didn't know about certain forces that we'll talk about in this minute. But anyway, Newton says that an object's natural, or its tendency is to stay in its current state of motion. As I said, mass is a measure of inertia. If you have more mass, that means an object is harder to move. Duh, right? That's part of the reason. I mean, our football players are big because they're strong, but they're also big because it gives them a lot more inertia, that they're just harder to move when they have a lot of mass. All right? The next law of motion is called the law of acceleration. And this is probably what you know of when you think of Newton's laws. What do you think of when you think of Newton's laws? An equation? Right, F equals ma. So the force equals the mass times the acceleration. So what Newton said is that if you apply a force is a push or a pull, right? Third grade. Force is a push. I push on something or I pull on something. If I apply a force, I cause it to accelerate. Now let's just sort of define a few things here. First of all, the net force is the sum of all the forces. Or in particular, it is the vector sum of all the forces. So for example, if I have an object here and it has forces acting on it, let's say that one force has a value of 2. Hey, what do you think the unit for the force is? Like if you were going to name the unit for the force to honor its heritage, what unit would you give it? What? A Newton, right? Because it's Isaac Newton. He came up with the idea. So anyway, the force is 2 newtons. And then let's say that you also have an additional force that is 3 newtons. Then we would say that the net force is the sum of all those forces, 2 plus 3, that's equal to 5 newtons. However, let's say that we have an object that has 3 newtons in this direction and 2 newtons in this direction. What direction is it going to move? If I have one force pulling in this direction, one force pushing in that direction, which direction is it going to move, left or right? It's going to move to the right. So we would say here that the net force is 1 newton. The net force here is not 5, it's not 2 plus 3. The net force is going to be 3 minus 2, and that's equal to 1. We generally, when we think of our coordinate system, we let this be positive and this be negative. Right be positive, left be negative, up be positive, and down be negative. Okay? So that's our net force. A free body diagram, your book talks about this, I'm just going to abbreviate it. A free body diagram is simply a picture with all the forces, or a diagram with all the forces that are acting on it. So let's say I have a picture of me. That's me. Okay? What are the forces that are acting on me? I have a weight, right? That is the force due to gravity. We'll get to that in just a bit. But I have a force that's acting on me due to the gravitational pull of the Earth. What is the direction of that force? It's down. So I have a force that pulls down on me. I'm going to call that Fw for my weight. And we'll get to that. What is another force? Because you know what this tells me is that if I have F equals ma, and this is my weight, that means I'm zooming down towards the center of the Earth. Because I have a force, I must be accelerating. But look at me. Is my speed increasing? Because that's what acceleration describes. Is my speed increasing right now? So I must have another force. What's the other force that's acting on me? Something pushing up on me. What is it? It's the ground, right. So we'll talk about that. That's called the normal force. So I have 2 forces acting on me, the weight and the normal force. That's all a free body diagram is. It's just a description of all the forces. Now, if I'm a football player, I might have some other forces. Like I might have another guy that's pushing on me. What do I call it? The lineman is pushing on me in this direction. So I have a force in that direction. Now, if I don't balance that force with another force, then I'm going to go zooming back in that direction. So I can have another foot, say, the force that I apply, where I'm pushing back on them, that keeps me from moving backwards. A free body diagram is just a diagram with all the forces that are acting on that object. Okay? All right. And then I also want to talk a little bit about vector components, and we'll get to this. We're not going to treat vectors mathematically very much any more than this, where we just have 2 vectors that are in opposite directions or in the same direction. But we're not going to deal with them. You got to know trig, and it's kind of complicated, and we're not going to do any of that business. But I do want you to understand the idea of vector components. Let's say that I have a force that is in this direction. I have a force that's in this direction. that force has two components. That is, I can break up this force into two different directions. I can break it up into a force that is along this direction and a force that's along in this direction. I'm going to call this F sub x and this F sub y. So let's see how we're going to do this. Grab my thing there. So if I pull Haley in this direction, you just stay in your seat. But imagine that I'm pulling her. She's going to come in this direction. Alternatively, I could pull in this direction and then give her another string and pull in this direction, and she's still going to come in this direction. Y'all follow what I'm saying? If I pull with a force in this direction, it's going to cause the block to move off in this direction. But if I also pull with a force in this direction and at the same time a force in this direction, then it's still going to cause the block to move in that same direction. So the force F is equal to the force Fx and Fy. Now I'm going to draw these with vectors or with arrows on the top because an arrow denotes a vector quantity. And just to remind us that this isn't an algebraic sum, but it's what we call a vector sum. And that's a bit different. We're not going to get into how to do that, but it's a bit different than just adding up the numbers. Okay? So just know that every force vector has these components. We'll do some more with that in just a bit. And then acceleration and velocity. I've been kicking around this idea, but velocity is a change in position over time. Right? And Aristotle said that if you apply a force, then the velocity increases to some maximum value, and then it goes along at a constant velocity. So he says if you increase the force, your velocity gets bigger, but it's constant. Your velocity is like your speed. That's what's read on your speedometer of your car. Acceleration is a change in velocity over time. Right? Acceleration describes how your velocity changes. Velocity is measured in meters per second. Acceleration is measured, I've given you this before, but it's meters per second or meters per second squared. So if you have an acceleration of, say, 10 meters per second squared, every second your speed increases by 10 meters per second. So if you're accelerating at 10 meters per second squared, what is your speed after 5 seconds? What do y'all think? 10 meters per second per second. Every second, my speed goes up by 10 meters per second. So after 5 seconds, my speed then is, y'all know the answer. 50's right. Right. So 50, your speed, it goes 10. After a second, it's 20. After another second, it's 30, 40, and then 50. Okay, so that's sort of brief explanations of acceleration and velocity. We'll come back to that a bit. Now, the third law is called the law of reaction. This says that for every force, there's an equal and opposite force. We've already seen it in a couple of places. Where's the string? Taylor, right? Have the string again like Kaylee did. Well, if I pull in this direction, I'm applying a force in this direction. What is the equal but opposite force that's a pair up with this? I'm pulling in this direction. Which direction are you pulling? you're pulling the opposite direction. You can let go now. So if I pull in this direction, she pulls in that direction. It's called an action-reaction pair. It's kind of cool when you think about it, because Newton's third law, you know what it says? This is going to blow your mind again in this morning. It says that if you have one force, you must have another force. That there can never be a single isolated force. Right? So like if I push on the wall, I'm pushing on the wall, what's the reaction force? The wall's pushing back on me, right? So for any force that there is, there must be an equal and opposite force. These are called action-reaction pairs. We also saw it before where I was standing and y'all told me that I have the force due to weight. And what was the force that pushed up on me? Yeah, the ground. We call that the normal force. We'll get to that. Okay? So those are the three laws. I want to show you a video. I think this is where I want to show you the video. Yeah. I want to show you a video that describes sort of the Aristotelian view, because I know that, you know, I explain the three laws to you, and it seems to make sense, sort of, kind of, I think. But people still walk out of physics classrooms and they don't really understand how this applies, like, out in the natural world. But this video tries to take sort of what is the commonly held view and then describe it in terms of, you know, the Aristotelian view. So these are the incorrect laws of motion. This is a Veritasium video. I tell y'all I met him once, that dude. I did. Like, we went to this conference. Do you care? We went to this conference. It was the American Association of Physics Teachers, and he was like the keynote speaker because he's huge. He's like famous. And my wife and I were there. She's a physics professor. We sat up on the front row because we're like his biggest fans. We are, seriously. He's awesome. Although I like Physics Girl now. She's really awesome too. It's like we're her new groupies. But anyway, we sat right up on the front row, and he came down and he talked to us. And then he let us take a picture with him, like a selfie. And he was a really cool guy. He had the cool hair and cool dresser and all this, but he was a cool dresser. Yeah. All right. I'll show you the picture one day. I'll send it to you. That's fine. There we go. Sorry, I have to pause this because YouTube is. Okay, so he mentioned this, and let me just sort of reiterate this. For the third law, he talked about the Earth and the Moon, that if I have the Earth here and the Moon here, they both exert a force on one another, and Newton described this in a variety of ways. But the force that the Earth pulls on the Moon is the same as the Moon pulling back on the Earth. Or if you think of a truck, like running into a fly, does that ever happen to you? Or your car and you hit a fly on the windshield? This force that you exert on the fly is exactly the same as the force that the fly exerts on you. Now, it's tragic for the fly, and you're okay. But the forces, nonetheless, are still the same. Just because you're bigger doesn't mean you exert a bigger force. Like a big football player and a little football player, when they collide, they both exert the same force on one another. Now, what happens to the little football player? F is equal to ma, so does he get a big acceleration or a small acceleration? Big. He gets the same force, but he has a small mass, so the acceleration is big. Let me write that down. So F equals ma. So if my force is the same, but I have a small mass, that means I have a big acceleration. Okay, let's look at some different types of forces, and your book goes through each of these, and then we're going to do a little activity. What time we got? Okay, so some just sort of classes of forces. Weight is the force due to gravity. In short, we have the Earth here. If I stand on top of the Earth, there is a force due to the gravitational force of the Earth. There are forces between all objects of mass. In fact, Caroline and Haley, there's right now a force between the two of you. Now it's minuscule, that's why you can't feel it. But you can measure it in the lab if you have very sensitive measurements, that you can measure the force between two objects of mass. Okay? So that's the weight is the force due to gravity. This force is equal to the mass times the acceleration due to gravity. We call it g. This is the acceleration due to gravity. And g has a value equal to 10 meters per second squared. And so we talk about mass and we talk about force, right? But those are two different things. Mass is a measure of an object's inertia, or a measure of the amount of substance that a material has. But a force is a measure of the gravitational force or the gravitational pull on that object. So, for example, if I have an object that has a mass of 10 kilograms, roughly, what's that, more than 20 pounds, then what is the weight? Well, the weight of this object is going to be 10 kilograms times 10 meters per second squared. That's this acceleration, or 100 newtons. And so we have measures of mass and we have measures of force, and those are very similar. They're related to one another, but they are different. In the British system, which is what we often use, what is our measurement for mass? No, it's not grams. That's the CGS system. In the British system, which we use, what's the measurement for mass? That's the MKS system. What? No. Nobody knows what the measurement. It's the slug is the measurement for mass. But what is the measurement for force? We all know that. How do we express our weight? In pounds, right. So in the British system, pounds is a measurement for weight, not mass. Follow me on that? Okay, we usually use it sort of in, what's the word? Like we'll use it in place of mass often, but it's really a measurement of weight, and those are two different things. Okay? The normal force, we've already talked about this, but the normal force is a force that is perpendicular to the surface. So, talked about this earlier. If I have I have a gravitational force that's down. The normal force is the force of the floor that's pushing up. And if I look at the floor, there's actually a force that pushes onto my feet, and that is the normal force. There's also a normal force underneath you right now that's pushing up on you that keeps you from flying down towards the center of the Earth. We can change the normal force. Often the normal force is equal to the weight. But not always. When we have two ways that we can change our normal force, we can change it, our normal force, and we're going to do this. We'll just sort of try this out as a class. These are just some bathroom scales. Bathroom scales, they don't measure your weight. Did you know that? Did you know they don't measure your weight? It's true. They don't measure your weight at all. Instead, they measure what? No. They measure the normal force. They measure the force that pushes back up. And if you're standing on this thing, then, the normal force, your weight is pushing down, but the scale tells me what is the normal force. Now, if I'm just like this, then my normal force is the same. But I can change what the scale reads. Am I right about that? You ever done this? You can jump up and down like this because I'm accelerating, and that changes sort of the net force, the total forces. I can push on something down like this. This is a pulley push-down machine over in the rec center, and I have the normal force, which is pushing up here, the weight, and then I have this additional force. Is my normal force here going to be bigger, smaller, or equal to the weight? Don't answer that, but we're going to think about it, okay? What I want you to do is you're going to break into, let's see, how many scales do I have? 5 scales. So you're going to have sort of 4 or 5 people in a group, 5-ish people in a group. Listen, if you're funny, I know some people don't like to share their weight with people, and I'm okay with that. So just find somebody in your group that's okay with that, and one person will step on the scale, and they'll say, gosh, my normal force is this. And then I want you to think about some ways that you can change your normal force. Are y'all comfortable with that? Is that okay? All right. Let's try it. What are some ways that you can change the normal force? Y'all try it out. So put yourself into groups of 5, and then come up and get a scale. We'll just spend a few minutes doing this, so about 5 minutes. Look, I'll put us, are y'all in a group? Okay, a group of 5, so you need to grab 3 more people. Y'all want to join these 2 ladies? Or you already have a group of 5? Okay. You might need to take on somebody else. Are y'all in a group of 5 right here? Awesome. Easy. All right, so y'all go grab a scale, and you're going to show some ways that you can change your normal force. Just a few minutes we're going to spend on it. Y'all need a scale? Okay, you just sort of have to, we can get one of you come up here, one of you maybe join these ladies, and one of you go over there, okay? Well, let's get up out of our seats and we'll go over. And can y'all take on a, oh, you have an extra. Y'all have an extra? Okay, yeah. Okay. All right, so think about what are the ways that you can change the normal force. What are y'all coming up with? Several of you said a couple different ways that you can increase or decrease your normal force. The first that people came up with, gosh, you just add weight, right? You put a book bag on, you put something in your arms, that increases the normal force. And what that looks like is, here's me standing on the scale, and then I hold a box. And so now I have two forces that are acting down. I have my force weight, and I have the force weight of the box, or whatever it is that you're holding. And then the net force, as a result, going up is bigger. It makes your normal force bigger, right? That's a vector sum. And the vectors that are going up, let me turn this light off. The vectors that are going up are going to be the sum of the two downward pointing vectors. We say that the net force is 0, because this force plus these two forces is equal to 0. Another one, I hadn't thought of this, but several of you found that if I stand here, and I'm about 175 or so, 180, but if I go down like this, my force normal drops to like 155. And that's kind of curious. Have you thought about that, why that is? Right. So effectively, your weight is being broken into two separate components. I have my weight. Part of it is pointing down, and that's what the scale measures. And then another part of it is on the wall. It's going in that direction. And so I have two normal forces in that case. I have the normal force of the scale, and what's the other normal force? The wall, right? There's an exercise, actually, right? These wall push-ups, you ever do that? It's sort of like an easy push-up. But it also does different muscles, too. Okay? Um, let's see. Let's save the inclined planes for next time, and we'll go on to friction. Although I have here, this is sort of getting into that, is that I have, this is my wife. Don't know that? We have an article coming out on this next month, and this is one of the pictures that we have in it, and I told her that I bet that your picture is going to be in the cover of this, and she's going to be a cover girl. Isn't that cool? Did I tell y'all it's our anniversary yesterday? 14, thank you. It's been a fun 14 years. Like, she's really fun to live with. I don't know if there's a single day that goes by without laugh about them. Okay? What was I talking about? Cover girl. Oh, components of forces. So here, this is like the scale when I go like this. There's a force. This is a, what's this called? What's this called? It's not a leg press, hack squat. It's called the hack squat, right? Hack squat? Nobody knows. Come on, y'all are athletic trainers for crying out loud. Okay. This isn't a leg press. Leg press is you're sitting with your back down. It's a hack squat. Thank you. What did I say? Hack squat. And what did you say? Hack squat. That's right. So in this case, you have a weight that you put onto the hack squat, but you're not lifting. Say you put 90 pounds on the hack squat. You're not actually lifting 90 pounds. You're only lifting a component of that weight. Kind of like when the scale reads less when you lean over. You're only lifting a component of that weight. We'll do some incline planes next time. Let's not worry about that too much right now. Okay, so with moving on, we have one other type of force that we'll talk about, and that is the frictional force. There are two types of friction. We have static and kinetic. The value for friction, this is the variable that we'll use for friction. It is equal to a coefficient times the normal force. Let's say that we're looking at static friction. Or no, we'll do kinetic friction. Kinetic friction is equal to mu k times the normal force. This is the Greek letter mu, like in pi mu, and but the lowercase Greek letter. And it is the coefficient of kinetic friction. a similar way, for static friction, which we're going to use Fs, it's equal to mu s times the normal force. So we have different coefficients of kinetic and static friction. Static friction means that there are two objects coming together. You know, friction occurs when you have two objects that are moving with respect to one another or when they touch one another. Static friction means that the two objects are doing what? Or not doing what, rather? Not moving. So these are not moving. And kinetic, I mean, you all know what kinetic means that they're doing what? Moving, right. So like in kinesiology or kinesthetic, it means motion, that root. So moving. So if I have an object that's not moving, there is a frictional force, because watch. If I push on this scale, I'm pushing on it right now. I'm applying a force in that direction. Why is it not moving? I'm applying a force to it. It should be accelerating by Newton's second law. Why is that? There's a frictional force. Is that static or kinetic friction? That's static, because it's not moving. If I push it, it travels a little ways, and then it stops. Why does it stop? What force is acting upon it? Okay, gravity is acting upon it, but what is the force that's causing it to slow down? Kinetic friction, right. Kinetic friction is friction between two surfaces that are moving with respect to one another, and static friction is between two surfaces that are not moving with respect to one another. You ever think about the cars on your tires on your car? Right, they have friction between you and the road. Which is it? Is it static or kinetic friction? The road's not moving. Now think about that. What is it? It's not obvious right away. I mean, the car is moving. The tires are spinning. The road's not moving, or the road stays where it is. You think static? I don't know what I think. I'm not sure. I have to think about this for a minute. I think that it's going to be static. Because when you think about it, the tire, it rotates, right? But the surface of the tire does not slide with respect to the surface of the road. Am I right about that? Right. It's not skids on your car. They're tires. They turn. It doesn't slide, so it's not kinetic. Instead, your tire rotates. So at any point, the surface of your tire does not move with respect to the surface of the road. Ah, that would be kinetic. Right. So this brings up an interesting thing, because it turns out that the coefficient of kinetic friction is less than the coefficient of static friction. You know this, that the static frictional force is bigger than the kinetic frictional force, because if you've ever had a big piece of furniture and you try to push it, it's hard to push at first, right? You had a couch or something, you're moving across the floor. Initially, it's really hard to get moving, but then once you get it moving, it's easy to move. You're aware of that? Go home and move a big piece of furniture, and you'll see that it's a lot easier to move after it gets started, because the kinetic friction is less than the static friction. So let's think about your car, because in your car you can have either static or kinetic friction, right? As who said that? Mariah, right? As Mariah said that if you're hydroplane, then your wheels, they lock up and they start scooting across the surface. Or if you hit water, they can still turn, but you're still hydroplaning. That's very bad, because our kinetic friction between the tires and the road is less than the static friction. And you always want the most friction that you can have, right? So what do cars do in order to always ensure that you have static friction between the tires and the road? What kind of system do we have in our cars? You ever have any old cars, like from the 70s maybe? Anybody ever have an old car like that? No. What do you have to do when you want to stop in an old car, like when the roads are wet? Right, you have to pump the brake, right? You tap it lightly over and over and over again. You ever heard of the ABS? anti-lock braking system, that was like the precursor to the ABS. The anti-lock braking systems, which all of our cars have now, it's just your foot tapping the brake off and on, off and on, off and on. So by doing that, the wheel never locks up. Because in those old cars, if you slam on the brake, the wheels, they just stop turning. And then you slide across the road right into the ditch. But the anti-lock braking system, you slam on the brake and the car says, hold on, jackaroo. We don't want to do that. Instead, we're going to slow down the tire, take it off. Put the brake on, take it off. Put the brake on, take it off. On, off, on, off, on, off. So that your tire continues moving, but it slows down. Another thing, and I want you to try this as you leave here. You've probably never witnessed this before because I know that it's not a common behavior for you, is that when you come out, if you go out of Maidwood, for example, this street right out here, you come up to the bayou, I want you to try something a little different. You ready? You're going to stop at the stop sign. Okay? Come to a complete stop. And your friend will be in the next seat next to you, and they're like, dude, what are you doing? I'm going to stop at this stop sign. And what happens as you come to a stop in your car? You what now? I'm sorry. You keep moving. Okay, that's true. That's not what I'm getting at. What are we going to say? No, just when you come to a complete stop on your car, in your car. You jump backward. You sort of go whoop, and then you stop. Your car sort of jerks. You ever felt that before? That's because your brakes, which are a pad against the rotor, they're exerting kinetic friction as your wheels are turning. But when your wheels stop, it's not kinetic, it's what kind of friction? Static friction. And that static friction is different from the kinetic frictional force. It's more. And so when you have this transition from kinetic to static friction, your car sort of lurches forward a little bit because you have that discontinuity. You have this transition between two forces. So with your friend, first they're going to be blown away because you're stopping at the stop sign, right? And then you explain to them, well, you know that kinetic friction is always smaller than static friction. And that's what's caused this discontinuity in our motion, that we sort of lurch forward. And they're going to think, gosh, you are the coolest person that I know. All right. So that's friction. Kinetic friction is smaller than static friction. This is the idea behind anti-lock braking systems. And also stopping at a stop sign. I'll just put stop sign. All right. Another thing, notice that the frictional force is dependent upon the normal force as well. Let's see here. No, help me out here. All right, so can you move your book? All right, so put your hand down on here. Actually, let's see, you just pull this out. Not so fast, goodness. Just sort of pull it, all right? So look, she was pulling the paper. It had a frictional force because, you know, the paper and the desk, there's some coefficient of, what was that, static or kinetic friction? It was moving, so it's what? Kinetic, right? Initially it was static, but then it turned to kinetic. So I was applying some normal force, which caused the friction to increase. But now let's try, I'm going to apply more normal force. Well, come on. What are you doing? What are you, a baby? Hey, you tore my notes. Well, that wasn't important anyway. All right. So if you increase the normal force, you increase the friction. And that's why on some vehicles, you know, you'll have these extra weights on them. It increases the frictional forces. All right? Okay, so tension, not much about tension, but they will come up with muscles, so it's kind of important. Ropes and cables and what have you can redirect forces. So for example, let's say that I have this cable here. I apply one force to this end, and as a result, I get the same force on the other end. This is called a tension force. And that force, whatever force I exert on this end, is found on this end. And all throughout the cable or the rope or the muscle or the ligament, I have that same force. And so this becomes relevant because, you know, if I apply a force up here, it's connected down here. Whatever force I apply here, I get the same force down here. So follow me on that? That's really all you need to know about tension. That we have these forces and they're equal throughout this thing. Okay, let's try these clicker questions. We'll try the one on the left first. The force in your bicep muscle attached at your shoulder and forearm is called a what type of force? Is that a frictional force, a weight, a tension, or is it a normal force? All right, we'll stop at 38. 38. I know not all of you have clickers. Y'all try to get clickers, okay? Borrow them from a friend or order them online or go to the bookstore. They're a little more expensive at the bookstore, but you can get them for not very much on Amazon. Okay, let's see. C is right. That's a tension force. That anytime I talk about our muscles or our ligaments, that's going to be a tension force. And then let's try this Newton's third law question, one on the right. All right, we will stop at 30. I got this down. Good. A is right. In fact, that's Newton's third law. The second one is which law? The second, the law of acceleration. And then this C is, right, the law of, what do we call it? The law of inertia, right. The law of inertia, law of acceleration, and then the law of reaction. Those are action-reaction pairs. And what do you call a guy, a normal guy, with a car on his head? Jack. You get it because of Jack. Okay. All right. We're going to move on with torques. The next time we're going to do some stuff with inclined planes. We don't have enough time to do it now, but we'll do it next time. But we'll go ahead and move on with torques for the next few minutes, okay? So forces cause acceleration in a line. Torques, in a similar way, cause it means acceleration, cause acceleration in a circle. So you can think of torque sort of as a circular force. That if I apply a force to something, it makes it accelerate in a straight line. If I apply a torque to something, it makes it accelerate in a circular path. They're very similar. You're probably familiar with torques. You experience torques. You might not know sort of the nomenclature, but you do experience them. And they're pretty important in how the muscles act in the body and the forces that they exert. Just a few little definitions. When not rotating, when an object's not rotating, the net torque, and torque, we're going to use the Greek letter tau. The net torque equals 0. That is to say, the sum of all the torques equals to 0. Just like we did with forces. In fact, we could say a very similar thing for for this when not accelerating, the net force is equal to 0. All right, let's try this. So our torque is equal to the force times the length of the moment arm. So say, for example, I have an object. It's allowed to rotate about this point. I apply a force at this point. Let's say I apply it as 2 newtons, and I have a distance here of 3 meters. My torque here would be equal to 2 newtons times 3 meters. That's the distance from where the force is applied to the axis of rotation. This is the axis of rotation. And so that's going to be 6 newton meters. My torque is 6 newton meters. We'll see actually the torque can change a little bit, and I'll give you a different expression for torque next time. But for now, let's just stick with this. So what is the force required? This is a lever, and we'll deal with some levers. What is the force required to hold this object in place? Let's say that if I applied a force right here, what force would be required there to hold that object in place? Okay, it wouldn't be 2. I understand what you're saying. Let's think for just a moment about what we're asking for. We're asking about a force. All right, so I have a 2 kilogram block on the left side. What force is required on the right side? You're sort of right with 2, but not exactly. I know what step in this. What's the force on the left-hand side? What is it, motion? No, it's not 8. What's the force on the left-hand side? Yeah. So there's a force. This object exerts a force on this side. What is that force? What is this measure? What is this? Describe the word. What is this a measure of? 2 kilograms. That's the object's what? Mass, right. So what is the force that it's exerting? Okay, let me show you. Okay, it's sort of new. The force, which is the force weight, is equal to m times g. That's 2 kilograms times 10 meters per second squared, so 20 newtons. And so I know what y'all are thinking, that I'll have 2 kilograms over here to balance this. I'm going to have 2 kilograms over here as well. But I actually need a force of 20 newtons. And I can find that mathematically. I would say that the torque on the left-hand side has to equal the torque on the right-hand side, so that the net torque would be 0. This would be 20 newtons times 2 meters equals to the force times where it's applied, which is 2 meters, and that force then, solving that, is going to be 20 newtons, because the 2's cancel out. The 10 is the acceleration due to gravity. So it comes back to this idea that weight is our mass times g. So if you look back at the weight, whenever we know the mass, the weight is actually that times 10 meters per second squared. It comes from Newton's second law, F equals ma. All right, now let's say I want to know what force is required right here. What force is required at that point, at some point that is equidistant from here to here. So at the halfway point, what is that force? I'll just think for a couple minutes. We're almost done, right? I want to take a stab at that. What do you think that force is? Is it going to be bigger, smaller, or the same as 20 newtons? It's going to be bigger. By how much is it going to be bigger? By 2. So what's the value going to be? 40. Right. So the weight then, or excuse me, the force required at this point, which is 1 meter from the axis of rotation, is going to be 40 newtons. And look, we can find that more rigorously if we just sort of want to process. We say torque on the left equals torque on the right. So I have still 20 newtons times 2 meters equals to my force times 1 meter. That's 40 Newton meters, 40 newtons equals the force. The masses cancel out. Okay? So that is our torque. We will stop there. We're going to do a couple of activities next time, and we'll look at inclined planes too, sort of going back to vectors. Okay, people, have a great day. Okay, I'll see you on Tuesday. Remember, we're going to have our quiz, our reading quiz, at the beginning of class on Tuesday.